K.U.Leuven, Belgium in 2011 to 2012, a visiting researcher at INESC-Porto, Portugal in 2014, and a postdoctoral researcher at RWTH Aachen University in 2014-2015. Currently, he conducts research on power system protection and control, electric power quality, as well as smart grid solutions, where he has published about 100 papers in peer-reviewed magazines and congresses. Thank you, Dr. Flávio.
Thank you very much. Good morning. I'd like to thank Professors Damasceno, João Paulo, Kleber, Felipe for inviting me. And I will talk a little bit about protection for smart grids. Here we have the conventional electrical power system. It's mainly composed by a generation, transmission, and distribution systems. The generation usually presents high power generators far from the loads. And the transmission system, we have here long transmission lines, usually AC transmission lines, connecting the generation to the distribution. And at the distribution, we have the power delivering to the load. Here, regarding the protection system, we have several conventional protections, such as overcurrent, directional, distance, differential, under overvoltage protection, frequency, and so on. The combination of such a protection systems is very accurate. However, the conventional electrical power system is going toward the smart grids. And in the smart grid, we have remarkable changes. For instance, we have high penetration of renewables, for instance, photovoltaic and wind energy. We have energy storage, for instance. And we have the concept of distributed generation. It's not new, but we have also the microgrids, for instance. And we have changes in the transmission power system. For instance, both AC and DC lines will be common, and probably we will have a Second World War of currents, of course. And but in this war, both AC and DC lines will win. Both will be common. We have electric cars. For instance, thousands of electric cars with powerful batteries connected to the power system. So these, the smart grid of the future will challenge large fields. For instance, the protection system. Hot topics. For instance, we have power system protection, power system control, power system automation and energy efficiency, power electronic, which is one of the pillars of the smart grids, supporting renewables, HVDC, MVDC, energy storage, electric transportation. We have sensors, smart metering, information technology, and power system communication, another pillar of the smart grid. So we have several hot topics in the smart grids, and I will talk a little bit about power system protection. In the smart grids, the conventional protections, such as overcurrent, directional, differential, and so on, all of them will be common, all of them will be used because these protections are very accurate. However, most of this protection is not so fast. So new ideas have to be proposed in order to to make this protection faster, okay? And on the other hand, new protection methodologies has to be proposed. For instance, I would like to highlight traveling wave-based protection. Currently, we have commercial traveling wave-based protection. However, new solutions are necessary. The island protection as well. So, in the smart grid, the integration of control and protection is essential. For instance, microgrids. And in order to propose new protection methodology, as well as to improve the conventional one, new mathematical tools are necessary. And for instance, modern signal processing, artificial intelligence, and other mathematical tools are necessary in this scenario of a smart grid. I will show you some examples of new proposal for protection by using the Wavelet Transform, but like I told you, a lot of possibilities are possible. By using the Wavelet Transform, there are several versions of the Wavelet Transform. For instance, the continuous Wavelet Transform, the discrete Wavelet Transform, stationary packet Wavelet Transform, stationary packet Wavelet Transform, and recently the boundary Wavelet Transform. The ideas are similar. For instance, here we have stationary packet Wavelet Transform. We have the original signal, and this signal is decomposed in several signals. So the wavelet information, we have several wavelet information. And the combination of this information can be used in several applications. The main advantage of the Wavelet Transform regarding the Fourier transform is its time frequency information. The real-time implementation is very simple, and the Wavelet Transform can be used in medium and high sample frequency. This can accelerate the performance of the protection system. For instance, the Wavelet Transform has been successfully used for high-speed fault diagnosis, include fault detection, fault classification, and fault location. The wavelet can provide high-speed fault diagnosis in the order of microseconds. And the wavelet can also be used for power quality diagnosis. For instance, it's possible to detect voltage sags well, transients. It's possible to detect flickers, partial discharge, and it's possible to estimate in the real time power quantities and the harmonic distortions. It's possible to estimate frequency, phase angle, and so on. It's possible to apply the wavelet for the noise. And the Wavelet Transform has been proposed in the protection recently. For instance, in the Overcurrent Protection, the Wavelet Transform can recreate the conventional protection, but with additional information. For instance, the Overcurrent Protection, the Directional Protection, Under and Over Voltage Protection, Differential Protection, Traveling Wave Protection, Frequency Protection, Distance Protection, and so on. I will show you some examples by using actual data or getting results experimentally. For instance, here, regarding the overcurrent protection, here we have a complex power system composed by a distribution power system with distributed generators here, and connected to a transmission power system. And we have a relay here and a fault here. And in this case, we have a single phase to ground fault at phase A here. And the performance of the conventional overcurrent protection was compared to the wavelet-based version of the overcurrent protection. Here we have the comparison of the performance, phase and neutral units, and the wavelet and the Fourier answer are similar. However, the wavelet was a little bit more fast, but the performance, the general feature were the same. However, the wavelet transform has additional information, such as that, and the conventional protection based on Fourier, there is no this information. However, by using the wavelet transform, you have the almost instantaneously, you have the fault detection, and we have the fault classification, sometimes the fault location. So this information can be useful in order to accelerate the overcurrent protection. Regarding the directional protection, the wavelet transform can also be used for recreate this kind of protection. For instance, here we have the power factor estimated by Fourier and estimated by the wavelet transform. The general performance is similar. However, the wavelet transform has additional information here that could be used for accelerating this kind of protection. Here we have a forward fault, sorry, and both of them could verify the directionality properly. Regarding a backyard fault, one more time, both of them could identify the position of the fault, and the directional, both directional and overcurrent protection could be recreated by using the wavelet transform. This is one possibility. So the power system protection needs an accurate methodology, an accurate method, and by using the wavelet transform, you can get the answer similar to the conventional one with the same accuracy, however, with additional information, which can be used for accelerating the protection. For instance, here we have the fault classification by using the wavelet transform. Here we have the wavelet information from phase A, B, C, and neutral. And in few microseconds, we can classify the fault easily. Each kind of fault, the wavelet information for each kind of fault is located in a specific region, and the fault can be performed successfully. For instance, the wavelet transform can also be used for power quality diagnosis in the real time. Here we have a voltage sag. Here we can see the voltage sag starting here. This is the end time. And by using the conventional RMS voltage, the voltage sag can be detected in the real time, however, with a specific delay. By using the wavelet transform, the same information can be obtained by using the energy of the voltage, for instance, by using the energy of the scaling coefficient energy, we can get the same information, but in different level. But the same information can be obtained with the same advantage and disadvantage. However, by using the additional information from the wavelet, we can detect the begin of the voltage sag and the exact end of the voltage sag. So the under voltage protection can be recreated, but with additional information which can be useful for accelerated protections. Here we have experimental analysis. Here we have a nonlinear load, and the wavelet transform could be used for harmonic distortion as well as power estimation. For instance, active power, reactive power could be estimated in the real time in accordance with the IEEE standard by using the Fourier. So, such information can be useful in a microgrid environment, for instance. Here in our laboratory, we have a microgrid. Microgrid comprises a small portion of voltage, of low voltage distribution system with several energy sources, such as photovoltaics, wind energy. We have storage device and flexible loads. And the microgrid can connect or disconnect it from the grid in order to operate, both in grid connected or in island mode. In our microgrid, we have 3 photovoltaic systems. We have a synchronous generator emulating a hydropower, and we have a small wind generator. And we have linear loads and nonlinear loads, and the microgrid is connected to the grid, to the main grid. And in this case, the wavelet information can be useful for both control and the protection. In this environment, both control and protection must work together. For instance, if you have a fault in the main grid, the protection system must detect this fault and disconnect the microgrid as soon as possible. So the microgrid should work normally during a specific time according to its capacity. And if the generation is not able to feed all the loads, specific loads could be disconnected. There is no problem in this case. But important loads, such as, for instance, a hospital, traffic lights, should be fed, okay? And so the control and the protection must work together. In this case, we have here an active power, which was estimated by using the wavelet transform. Here we could detect the low frequency oscillation in the synchronous machine, for instance. And the control used such information in order to get the stabilization of the machine. For instance, if a fault takes place here in the main grid, and the protection system does not trip so fast, the small generator should be stable even in a fault situation. So the control should work well here in order, because if the synchronous generator, for instance, lost stability, the protection, the microgrid will not run in an island mode successfully. So in this case, the wavelet transform could be used in order to, could be used in a PSS, power system stabilization, in the control system. The wavelet transform, the information such as power estimation, harmonic estimation, is very important for control as well as for protection. Regarding the island protection, the wavelet-based overcurrent, directional, under voltage, and so on, could be used in these scenarios. We have here another example. Here we have a high impedance fault, which are dangerous because this kind of fault is common here in Brazil. And for instance, Brazilian death is so high here. For instance, in 2015, 53 persons died here in Brazil. And the high impedance fault has some particularities. For instance, we have a lot of information here. The overcurrent is not so high, so the conventional protection usually is not able to detect all the high impedance faults, but we have several information here that modern signal processing could detect such information. For instance, by using the Wavelet Transform, here we have an actual case of high impedance fault. By using a conventional Wavelet Transform, the fault could not be detected. However, by using the boundary Wavelet Transform, a version of the Wavelet Transform, the high impedance fault could be detected successfully here. Another example is a power transformer whose the main protection system is composed by differential protection, as well as other kind of protection, such as overcurrent protection. However, the trip is in the order of few milliseconds. However, by using the Wavelet Transform, this kind of protection could be recreated, wavelet-based differential protection, and with the same performance, similar performance, however, much more faster. For instance, here, the trip was reduced to the order of few microseconds. Here we have some examples, for instance, an external fault here and an internal fault in the power transformer. By using the wavelet information, the restraint energy obtained with the Wavelet Transform present this feature. However, in an internal fault, the blue line, which is the operational energy, could increase so fast. Here, the fault, external and internal fault, could be differentiated and could be detected in microseconds. Here is another example. This is a critical internal fault in a power transformer that the conventional one could not detect it. However, by using the Wavelet Transform, which is very sensible to transients, could detect this kind of fault. The Wavelet Transform can also detect the current transform saturation. So during the current transform saturation, the protection can be blocked. However, if an internal fault takes place, the wavelet-based protection can detect and can trip this protection. The transformer can be protected. Another situation in a smart grid is a high voltage DC power system, for instance. Here we have some examples. HVDC transmission line. This kind of transmission line, this kind of system can be used for connection of offshore renewables to onshore AC networks. It can be used in unsynchronized AC networks in order to connect them, as well as in network, as well as to link networks of different frequencies, and so on. And one kind of protection, a possible protection for this power system is by using the traveling wave. I will show you some examples. The traveling waves can be used in both AC and DC lines. Here we have an AC line, and by using the traveling waves, when a fault takes place in the protected line, the wave propagates in both directions toward the line terminals, and the fault inception time at these bars takes place here. However, the beginning of the fault at the remote line takes place here. In this case, by using the wavelet transform, you can detect the beginning of the fault here and the beginning of the fault here. And by using the combination of this information, the fault can be located as fast, very fast, and the protection of the transmission line can be performed. However, it's necessary communication equipment as well as data synchronization. However, there are other possibilities. A traveling wave-based protection by using just information from the single line, from the single terminal. Here, it's necessary to detect the beginning of the fault as well as to detect the reflection from the fault point. If you detect, by detecting both information, time information, it's possible to locate the fault, identifies the fault is on the protected line and performing the protection of the line. However, there are several problems here. The first one, it's not so easy to detect this information. Modern signal processing is necessary. For instance, if the fault is near the remote bus, the goal is to detect this wave, and this wave, however, other wave can first, and it's necessary to detect and distinguish this kind of information. By using the wavelet transform, it's possible to detect them. Here, it's possible to detect the beginning of the fault in each bus terminal. It's possible to identify the directionality too. Here is an HVDC power system, and in this example, it's possible to detect by using the wavelet transform the surge time incidence, and it's possible to locate the fault with a high precision, with a high accuracy, and it's possible to perform a high-speed protection. Here is the protection in this converter station. So it was a pleasure to be here, and thank you very much for your attention.
Thank you, Professor Flávio. I'm now opening the session for questions. Professor Notzig.
I appreciate that wavelets are so useful in these applications. Could you elaborate on with what kind of sampling rate are the signals taken from the grid and then be processed in that wavelet tree, and what kind of order of the wavelets you have used there?
Okay. The sampling rate, by using the wavelet transform, it's possible to use high sampling rate, and in this case, in such analysis, most of if the conventional power power system protection is the goal, to be recreated at 20 kilohertz was enough for the wavelet transform. It's there are commercial relays with sample rate in this order. However, if the goal is to detect the fault by using traveling waves, for instance, it's necessary a high sampling frequency. And the wavelet transform can be used with a high sampling frequency because the wavelet transform presents a good time frequency relationship, and it's possible to detect low frequency transients as well as high frequency transients. So by using traveling wave, it's necessary sampling frequency in the order of megahertz.
What kind of order the wavelet?
Okay, sorry. In this case, I have been used a new version of the wavelet transform. It's the boundary wavelet transform, because this kind of this wavelet transform was designed in order to be used in the power system protection, and the mother wave was the B.Sc mother wavelet with 4 coefficients. The Haar wavelet is also possible.
Thank you very much.
Thank you.
Thank you, Professor Flávio. We have 2 more questions. Two, actually.
Well, just one. We have a very fast detection, but the electronic system is ready to react at the same velocity?
I think so, because most of these examples, the wavelet transform was implemented in the hardware, and I don't remember here, but the computational burden was very low. I don't remember, but I think 1 microsecond it's necessary to compute the wavelet information.
Very fast.
By using a normal DSP.
Thanks.
Briefly, congratulations, Flávio, for
Thank you.
the presentation. Could you comment about technology to implement this type of protection?
Technology about
Is to implement type of hardware.
Oh, okay. And there is no technological problems by using low sampling frequency in the order of 20 kilohertz, for instance. But by using high sampling frequency, for instance, in the traveling waves, it's necessary a high sampling frequency. So it's necessary to use for instance, a current transformer with a high sampling, with a high frequency spread, and maybe if you need a very high sampling frequency, optical transducers could be used. So it's a very new application, and there are some technological problems, and solutions have become every day in these questions to solve these problems. But the way to get the information is one of the main concern, because if the transducer didn't answer to a high sampling frequency, if the high sampling frequency is filtered, so you cannot detect the traveling waves successfully.
Okay, thank you very much. Another round of applause. Okay, I'm going to pass to the new chair, Professor Felipe. But before that, a brief announcement. After the last talk of the power session system,